All right, let's talk about this really fancy word, order of magnitude. The definition is as follows. An order of magnitude estimate specifies only a broad range of values, such as in the 10,000s or in the millions. So if I wanted you to get something correct to a particular order of magnitude, basically I would want you to get it correct. If the answer was 75 million, I would want you to at least know that it was in the millions, right? And an increase in an order of magnitude is equivalent to 10 to the n. So basically, 2513 is a particular order of magnitude, and it's one magnitude larger than 251.3. Okay, 1000 is one magnitude smaller than 10,000. All right, so you're just trying to get to the right order of magnitude sometimes when you're answering questions. For example, if I asked you how many students are there in the United States, and I want the answer correct to the correct order of magnitude, is the answer in the millions? Is it in the billions? Is it in the trillions? So that's what I'm talking about when I'm talking about order of magnitude. I'm not asking for a specific number like 350,276,000. I'm looking to be the right order of magnitude. Make an order of magnitude estimate of the total annual spending on ice cream in the United States. So here's some information. An average person eats around 50 servings of ice cream per year. There are 300 million people in the United States, and ice cream costs $1 per serving. All right, so we are doing 300 million times 50, which we certainly could do with scientific notation, but I think it's not too bad to just say 300 million looks like this, and then multiply that by 50. So all we really have to do here is do 3 times 5 is 15. And then we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so I'm going to bring back my commas. All right, so what's my answer here? If ice cream costs $1 per serving, which is not true, but gives us a rough estimate, we're essentially spending $15 billion on ice cream. Well, what's the correct answer? 13.7 billion. So we're not exactly correct, but we're at least at the right magnitude, the right order of magnitude. How much money are U.S. students paying for school supplies? Well, here's some info needed. About 50 million elementary and high school students exist. And I'm just going to do a rough estimate. I could be wrong here, but let's say that these 50 million students spend on average, I don't know, let's go with $50 on school supplies. To you, you might think of that and say, whoa, I don't spend anywhere close to 50. And some people say, whoa, I spend way more than that. But this is just an estimate. All right, well, let's do 5 times 5. That's 25. And then how many zeros do I have? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. All right, so what am I looking at here? I'm looking at 2.5 billion is my guess. Looks like I was a little bit off. But the question is, how far off was I? I argued that it was 2.5 billion. And I was off by 1 order of magnitude, which means in reality, I probably should have said that on average, students spend $500 a year on school supplies. So I guess that includes maybe clothes, computers, etc. So you can see that sometimes estimating gets us close, but sometimes you're off by 1 order of magnitude or maybe even more, but at least you're close. All right. Now we're going to talk about a brand new subject, and that is conceptualizing really big numbers. Oftentimes you think about something and it's hard to really think about because it's either so big or so small. So how tall is 1,000 feet? Can you visualize that? Well, what does it look like compared to something you know? If our school is 10 feet high, then 1,000 feet is 100 of our schools stacked on top of each other. To me, that gives me a slightly better idea of how tall 1,000 feet is. Or maybe we want to think about football fields. The other thing I'm thinking about is maybe a football field. A football field is 100 yards long, which is roughly around 360 feet. And so roughly, we are a little bit less than 3 football fields. So maybe that helps you a little bit more, 3 football fields. And this whole entire video is about estimating and getting close enough and being able to conceptualize something. So yeah, it's a little bit less than 3 football fields, but it gives us a general idea. How tall is 90 meters? Well, can we think of anything that is close to 90 meters? Well, I know that a basketball court is roughly 30 meters long. So I could think about 90 meters tall as being 3 basketball courts. Or when I was diving, I used to dive. This is my diving board picture. I hope you like it. There I am climbing up the ladder. And then I would go bounce and I would do flips and go into the water. And I would dive off the 3-meter platform. So to me, 90 meters would be best conceptualized by saying 90 meters divided by 3-meter platform equals 30 diving boards. So I would think about 90 meters as being 30 of me climbing up this 30 times. It's just giving yourself an idea of what something looks like. This is something you might want to write down in your notes. It could help us potentially do a homework problem or a test problem. These are some important conversions from metric into our US system. Let's talk about big numbers now, like really big numbers. What about saying that you earned $1 billion? How long would it take you to count your $1 billion if you count 1 bill a second? And that's reasonable, 1 bill a second. Well, first of all, how many seconds are in a billion? So, I'm trying to think. We've got 1 billion seconds. And I want to convert that into something I know. So there's it's going to take us 1 billion seconds to count our $1 billion. All right, well, let's convert that into days or minutes or whatever it is. So there's 60 seconds in 1 minute. And then there's 60 minutes in 1 day. Just kidding, in 1 hour. Silly goose. And then there's 24 hours in 1 day. So what have I done here? This is something you should be familiar with. Notice how I'm converting from a billion seconds to days. So I've said that there's 60 seconds in a minute, 1 hour and 60 minutes, and 1 day is 24 hours. And just watch how things cancel. The seconds cancel, the minutes cancel, the hours cancel. So I'm left with an answer of days, and it's going to be 1 billion over 1 times 1 over 60 times 1 over 60 times 1 over 24. When we multiply fractions, we just multiply straight across. So this is going to give me 1 billion. And then in the denominator, I have 60 times 24, which gives me 86,400. So now I'm going to do this math. And I get how many days? 11,574 days. That is how big $1 billion is. If you took a second to count every single bill for $1 billion, it would take you 11,574 days. Let's figure out how many years that is. Well, there's 365 days in a year. So if I divide that, we're talking roughly 32 years, a little bit less than that. That's how big $1 billion is. You're literally sitting down every second and counting your money, and that's for 32 years. And think about some of the richest people who have way more than $1 billion. All right, here's another one. In 2015, the federal budget was $3.8 trillion. The federal budget is the annual public expenditures of the United States. Help me understand this better. Well, maybe think about if we're spending $3.8 trillion, how much would each person get? Well, that would be 3.8 trillion would look like, let's see. So this is going to be hundreds, thousands, millions, billions, trillions. And we're talking about taking that amount of money and dividing it by our U.S. population, which is roughly 300 million. Hundreds, thousands, millions. So let me do that math real quickly. And I get 12,667 per person. So every person you drive by and all other people in every single state, Texas, Hawaii, Alaska, everywhere, New York City, basically the federal budget is going to be $12,667 per person. And that kind of helps me realize, wow, how much money the federal budget is. And so just a heads up kind of information here, you can see where our money goes. The majority of it is going into Medicare and healthcare. We're going into Social Security and unemployment labor. We've got money going into the military, and we've got interest on debt that we owe various countries. And then the rest is fairly small, including education is very small on this list, this being education right here. All right, I find this direction a little bit harder, but hopefully we can do this. You're going to say, this is ridiculously interesting when we're done with this problem. So let's go small. An atom has a diameter of 10 to the negative 10 meters. The nucleus of an atom has a diameter of 10 to the negative 15th meters. So let's say the atom's nucleus was the size of a marble, 1 centimeter. How big would the atom be compared to the marble? Well, first of all, we have to decide how much bigger the atom of the diameter of the atom is compared to the nucleus. So this number is bigger, right? If we think of 10 to the negative 10 power, I'm going to do that on my calculator real quick. That gives me 1 times 10 to the negative 10th, and we know what to do here. That's equal to 1.0 times 10 to the negative 10th. So I'm bringing my decimal back 10 times. So that's what that means. 10 to the negative 10th means we're bringing that decimal back 10 times. So 10 to the negative 10 is actually 0.000345678 and then a 1. All right, and then 10 to the negative 15 would be 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, would be that. And so you can see that this number is the bigger number divided by the smaller number. This is the size of our diameter of our atom, and this is the size of our diameter, the diameter of the nucleus. All right, so dividing these two numbers, let me tell you what I get. I get, and this makes total sense, 100,000. All right, so that means that if we look at our atom with our nucleus, okay, it actually means that this diameter right here is 100,000 times bigger than your nucleus. That's crazy. So my picture is so inaccurate. Even this picture right here with a little tiny thing, that is so inaccurate. So let's try to conceptualize this. If we say that the atom's nucleus is the size of a marble, 1 centimeter, okay, well, how big would the atom be? Well, that would be 100,000 centimeters. Okay, well, let's convert that and let's go back to our handy dandy chart. So we know that 100 centimeters is equal to 1 meter, and we know that 1,000 meters is equal to 1 kilometer, and 1,609 meters is equal to 1 mile. So let's see if we can convert this. All right, going back. All right, so I'm going to convert my 1,000 centimeters. So, 100,000 centimeters. So I know, from going back there, that there's 100 centimeters in 1 meter. I also know that there is 1,000 meters in 1 kilometer. So let's see if what we can do here. So we're taking 100,000, dividing it by 100, and then dividing it by 1,000. We actually get 1 kilometer. All right, so what do we have here? What we have is a marble, literally a marble, and then that's our nucleus of our cell. The actual size of the atom is going to be a kilometer. Okay, do you know how big a kilometer is? Let's see if I can come up with something similar. I think the best thing would be to compare it to miles, and 1 kilometer is roughly 0.6 miles. So what you have here is a marble for your nucleus, and then 0.6 miles would be how big the diameter of your atom is. Isn't that unbelievable how small your nucleus is? I know that was a long video, but I appreciate your time. I hope everyone has a great day.